All right, let's get started. It's a great pleasure for me to introduce Professor Enectali Figueroa-Feliciano. Tali got his PhD at Stanford University in 2001. And after that, he joined NASA Goddard Space Flight Center, working on putting ultra-sensitive microcalorimeters onto rockets and satellites. And since working at NASA wasn't challenging enough for Tali, he moved to MIT in 2006. There he started building Micro-X, high-resolution microcalorimeter X-ray imaging rocket. He also got involved in the dark matter direct detection experiment, SuperCDMS. Well, at that point, its name is still just simply CDMS. And he also started a coherent neutrino scattering experiment named Ricochet. So Tali moved to Northwestern University in 2015 and launched the Micro-X rocket in 2018. And it's the first time anybody put a transition edge sensor detector into space. He's now involved in a broad range of scientific topics, including X-ray astronomy, dark matter search, coherent neutrino scattering, neutrino-less double beta decay, and recently he got himself involved in quantum computing, all super cool stuff. So without further ado, let's have Tali tell us about his adventures in discovering new physics among dark matter and neutrinos.
Okay, thank you very much, Zicheng. My name is Enectali Figueroa-Feliciano, and that's a handful to say, so I go by Tali. I'm going to be talking to you about mostly dark matter, but some adventures in neutrinos and other things. So we'll start with some motivation, why studying dark matter is a cool thing to do. Then we'll go over the dark matter problem and how do we go about detecting dark matter. We'll talk about the efforts that we're doing in SuperCDMS to detect dark matter. Then we'll talk a little bit about our efforts in neutrinos. And if we have time, I'll talk about one more thing. All right, so we start off by asking the big questions. What is the universe made of? And that is an age-old question. It used to be that people thought the universe was made of air, water, earth, and fire. And then we've learned more, and we can now look at the periodic table of the elements, and we can have some order into all of the different elements that make up all the molecules that we see in our planet, in our universe. And we've learned that each of these elements is made up of protons and neutrons inside a nucleus, and they're surrounded by this ball of electrons. And the number of these particles that each element has can be arranged in this nice periodic form, and there are relationships between the different elements that we can learn. Now, as physicists and as particle physicists, we're trying to figure out what are the most fundamental parts of matter. And so we know that we have these electrons, and when we look, we find that the protons and neutrons are actually made up of even smaller things called quarks. And so there's this up quark and this down quark and the electron. And everything that we interact with, everything that we are, the whole planet, the solar system, when we look out of the sky, all of the stars that we see, they're all made up of these three particles. Now, just like in the periodic table, there are rare elements. There is a standard model of particle physics that's sort of our periodic table for particles that gives us a richer palette to draw upon. Now, these are fundamental particles that we don't see every day, but we can create at colliders. And it has been an amazing success. The standard model can predict the values of different fundamental parameters in a part billion. So it has been a very awesome success. And of course, one of the largest being the finding of the Higgs boson at the LHC. But the standard model is wrong. Unfortunately, it is not complete. It doesn't explain things that we know are there. For example, it doesn't explain what dark matter is. None of these particles, there's a bunch of them to pick from, none of these can be the dark matter. It also has neutrinos. So these guys down here are the neutrinos, but in the standard model, neutrinos have no mass. Yet we have measured neutrinos in experiments and we know that they do have mass. So the standard model doesn't explain why. The standard model doesn't explain why we're here. So in the standard model, you can make matter or you can make antimatter, and you would make both of them in equal amounts. So according to the standard model, all of the matter and antimatter would have annihilated at the beginning of the universe, and none of us would be here. So there's something missing in here that tells us why there's more matter than antimatter in the universe. There are other problems, like the fact that the universe is expanding and accelerating. We don't understand gravity. None of those things are part of this model. In my talk, in my work, I work primarily in trying to understand what is beyond their standard model and trying to answer these three questions. So if you think about the work that I do, I'm mostly focused on dark matter, but I also work on neutrinos. And I have different experiments that I'm working on. So one of them is SuperCDMS, which I'm going to spend most of the time today talking about. And then on the neutrino side, I'm involved in two experiments. One's called Ricochet, which is a coherent scattering experiment to measure neutrinos at a nuclear reactor. And the Cupid experiment, which is its follow-on to the very successful Quarry experiment, which is trying to find evidence for a particular process called neutrinoless double beta decay. In the overlap between dark matter and neutrinos, it's possible that some flavor of neutrinos might be dark matter, and we'll talk a little bit more about that. And there's the Micro-X rocket program, which is a NASA-funded sounding rocket program. And one of the things that we would like to do with this rocket is to search for dark matter in the form of sterile neutrinos. Now, in my talk today, I'm going to concentrate mostly on SuperCDMS and then talk a little bit about neutrinos. So I'm not going to talk about the rocket program. I just want to give a shout out to the folks that have worked on this rocket and show you a picture of what it looks like. It's an actual rocket. We launched it in 2018, and we are planning to launch it again next year. So this is a very exciting program, but it's mostly for doing astrophysics at this time. And so I'm not going to go into it more than this. And of course, the work that I'm showing and I'm going to talk about is really not done by me, it's done by the people in my group. And so I want to really give a shout out to them, especially the guy in the iPad that you see there, which you may recognize, who actually most of the stuff that I'm going to show is a direct result of his efforts. So I definitely want to recognize that Zicheng has, before he left us for Toronto, he really was the lead and the primary mover in my group making things happen. All right, so let's start talking about dark matter. So what is dark matter? Well, when you look out at the universe, you can count all of the matter that you see in the stars. But of course, there's things that don't shine, like rocks and dust. There might be planets that are pretty dark, but you can take into account all of that. So you can look at a galaxy and say, I see this many stars, and then I can add to that all of the dark stuff that I know is there, the dust, the planets, the rocks, the asteroids, all of that stuff. And with that, I can get a total mass for what this galaxy should be. Now, if you guys think about having a rock on the end of the string, and I spin the rock around, there's a tension on the spring, which is keeping the rock from flying away. And the faster I turn the rock, the stronger the tension of the spring. And that's why if you want to throw a rock really far, you have to spin it really fast. So by measuring the speed at which the stars are going around, that tells me how much force is keeping them going in orbit about the center of the galaxy. And that force is due to gravity. And gravity comes from mass. So the speed of those stars is related to the force they feel, the pull they feel, and that pull is a measure of how much mass there is inside of where the star is orbiting. So when I look at models of galaxies based on what we see, we expect them to be rotating in a certain way. But when we measure them, they're actually rotating a lot faster. And if they're rotating faster, they need to have a bigger force or they would fly apart. And that bigger force implies that there is a larger amount of mass. And this is the dark matter that we're talking about. It cannot be accounted to by asteroids or dust or meteorites or any other dark thing you can talk about. This is a new thing. And we think it's a new particle that hasn't been discovered yet. And we need a lot more of it. About 80% of all of the matter in the universe is dark matter. Now you can look at galaxies and see this effect. You can also see the effects of dark matter at the largest scale. So this is a picture of the cosmic microwave background. And the cosmic microwave background is a picture of light that has been streaming through the universe and gotten to the detector from only about 400,000 years after the Big Bang. Say, well, 400,000 years is a long time, but the universe is 13 and some billion years old. So if you think about the universe today as being 100 years old, this is a picture of when the universe was a day old. So this is really a baby picture of the universe. And you can see that there's all this red and blue stuff. Those are temperature differences. And you can see that it's not quite random. There's some more blue parts, some more red parts. You can turn this into a mathematical description of the relationship between these patches. And when you do that, you get what you see here in the right. So you get these curves that tell you the relationship between all of these spots with respect to the other. How often do I get a red spot so far away from another red spot? I'm not going to go into the details of this, but the point is that this encodes a lot of information about what the universe was at that early time. And you can make a model. You can see the line going through all the dots that really fits the data really well. And this model is called the lambda CDM model of cosmology, has 6 parameters. And this model fits all of the observations that we have of the universe. And it predicts and it requires there to be something called dark energy and something else called dark matter. So when you make a pie chart of the energy density of the stuff in the universe, you get something that looks like this. So most of the universe is dark energy. And more than a third of the universe, or almost a third of the universe, is dark matter. There's a bunch of helium and hydrogen floating around. And then there's like stars. And this really thin black line right here, that's 0.03% of the entire universe. That's the heavy elements. So that's things like planets, people, and most importantly, ice cream. And so what we thought we knew was there, all the stuff we saw, which was only this little bit, turns out to be a very small percentage of the universe. So as a very famous philosopher once said, you start down this dark path, forever will it dominate your destiny. So we've figured out through all these measurements that the things that we saw were just the surface of what was there. And we really live in this universe dominated by the dark side. And so 96% of everything that's in the universe is in this dark sector that we want to understand. So I hope you agree that this is a really beautiful problem in physics. It's really nice because it's a fundamental question about what the universe is made of. It also spans all of the scales that we can see in the universe, from the biggest scales of the cosmic microwave background through galaxy scales. And because we think it's a new fundamental particle, we can study it at the smallest scales we can measure in particle colliders. And so it's a really beautiful problem in physics that spans all of our available space, parameter space for searching. So let's talk about how to actually search for dark matter. So we can make dark matter, if dark matter is a new fundamental particle, at an accelerator. So there are searches that are going on where you try to collide protons together, like at the LHC, and you try to create dark matter and then see that dark matter and its products in the collider. So that's direct production in the colliders. You can look for the astrophysics measurements of dark matter, like the one from the galaxy that I showed a few slides ago, where you go measure the properties of galaxies or the cosmic microwave background, and you infer properties of dark matter from those astrophysical measurements. You can look at standard model particles like photons or muons or protons that are coming from space and might have been made by a interaction where dark matter took part. So that's called indirect detection. Maybe dark matter annihilates or it decays or it hits something and it generates an excess of particles that you can detect. And so you are actually detecting standard model particles, but you're trying to infer the existence of dark matter through that indirect channel. That's called indirect detection. Or you can try to detect the dark matter directly in a lab. So there are millions and millions of dark matter particles going through each of us every second. They go through us, they go through the entire planet, they go out the other side, they keep on going. And so every once in a while, one of those millions and millions of particles might actually hit one of the atoms in our body. So if we build a detector that's sensitive enough, we might be able to sense those rare events when a dark matter particle interacts in some way with our detector's atoms. And that's what we're going to be talking about, focusing on SuperCDMS. And of course, there are many different types of experiments trying to do this direct detection. So SuperCDMS stands for Cryogenic Dark Matter Search. It's a collaboration of about 100 scientists, which is small in particle physics, but large in other in other areas. I think, let's see, I'm over here. And we are going to put an experiment at the at Snow Lab, which you guys know all about. I got this picture from the Snow Lab website that shows that the laboratory is 2 kilometers underground. It's in Sudbury. And here's the CN Tower to give a scale, but of course, since I was giving, I'm from Chicago, I have no idea how big the CN Tower is. So I put the Willis Tower, which is the landmark building, and I was very disappointed to see that the Willis Tower was smaller than the CN Tower when I put them to scale, but there we go. So this is really deep underground, and the reason that we're going all the way down here is that there's cosmic rays, high energy gamma rays, all sorts of particles coming from the sky that are hitting the surface of the Earth. So this is the surface right here. And we're using these 2 kilometers of rock as a shield to stop all of those particles from getting down to the snow site. Inside the snow site, there's a network of caverns. And in those caverns, one of those caverns, we are building the SuperCDMS Snow Lab experiment. Now, even though we are 2 kilometers underground, the rock itself has trace radioactive elements, which would ruin our measurement. And so not only do we need to use the 2 kilometers of rock as a shield, but then we need to shield from all the rock that's around us, which has trace amounts of uranium, thorium, and other radioactive elements. So the detectors are in here. They look like this. They're a tower of detectors. We have 6 detectors per tower. And these detectors are surrounded by polyethylene and lead and water to shield them from the particles coming from the cavern. These detectors, as we're going to talk about in a minute, operate at cryogenic temperatures. So they need to be cooled down to thousandths of a degree above absolute zero with a dilution refrigerator. And then we have some complex superconducting electronics that need to be read out. So we have this complicated electronics readout tank connected to the system. And down in the mine, there can actually be earthquakes. So all of this thing is built upon a seismic platform that's designed to allow the earth to shake a little bit and not tear our experiment apart. So we're putting this experiment together, and we're planning to take first data in 2023. Now, we don't know what dark matter is, but we have to categorize what we're looking for somehow. And one of the ways we do that is by assuming what mass the particle of dark matter might have. And so on the x-axis here, there's a bunch of different masses. So you can, through E equals mc squared, if I have a mass m, I can assign to that mass an energy E. And that's what this is. So this is mass labeled as energy from 1 eV to 1 TeV. And just for reference, a proton, a neutron is about 1 GeV. And the experiment, through different interactions with our detector, is sensitive to dark matter in this entire range. Now I'm going to focus on the HPEV detectors, which are sensitive to masses a little bit below 1 GeV and forward. Okay, so how do our detectors work? So what we do is we have a target, some crystal that we want to use as a sensor, as a detector, and an event happens in the crystal. A particle comes in and hits it. When it hits it, it deposits some heat. It exchanges energy. We connect this to a very cold bath on a dilution refrigerator, usually 10 to 50 millikelvin. That's thousandths of a degree above absolute zero. We connect it through some thermal conductance G, and then we put a thermometer that senses the phonons in the crystal. Phonons are a fancy way of saying the vibrations in the crystal, just like if you had a hammer and you hit a bell with the hammer, the bell would vibrate. When a particle hits the crystal lattice vibrates, and we can call those vibrations phonons and then treat them, use that terminology to measure the heat that's deposited in this crystal. And so what we're basically doing is just measuring the temperature of this as a function of time. So if you look at it as a function of time, you're going to see the detector just sitting there. Then when an event happens, it's going to get hotter. And because it's connected to the refrigerator, it's going to cool down, and it's going to have some decay time, and you're going to get this pulse. So every one of those pulses tells us that an event happened, and the height of that pulse gives us an idea of the energy that was deposited. Now, we need a very sensitive thermometer, so we use transition-edge sensors, where you have a superconductor where you have resistance and temperature, and there's a critical temperature on that superconductor where the superconductor goes from normal resistance down to zero resistance, which is when it's superconducting. And so we operate in the edge, that transition edge of that transition. And so a small change in temperature makes a large change in resistance. And so by measuring out this resistance, we can measure out the sensor. And here's another picture of that process. So you're biased at some point, you get some increase in temperature that moves the detector up in this curve, and you get a large change in resistance. We read out that resistance with a very complicated superconducting circuit using squids, and different types of experiments use different configurations for these squids. TESs can be made out of different materials depending on the optimization. So we use molybdenum gold, we use tungsten, we use aluminum manganese. So it just depends on the actual application what your superconductor is made of. So here's a picture of one of our detectors, which I will talk more about. this is a cartoon of sort of what happens. So the event comes in and hits the crystal. And as we said, we whack the crystal like hitting a bell with a hammer. The crystal starts to vibrate. We can think of those as these phonons that are flying around the crystal. And then on the surface of the crystal, we have these aluminum pads which absorb the energy from these phonons. These aluminum pads are superconducting. There are things called Cooper pairs which absorb the energy and break up. And those particles, which we call quasi-particles, kind of diffuse through and get to the TES. Then the TES gets hot and we measure that signal. So it starts out simple, but of course, when you design things, it gets more complicated. This is a picture of what one of those units looks like. The light blue stuff is the aluminum, and the gray bar here is the actual TES. So if you think about a sensor, this is a cross-section of a detector. Particles coming in, it hits the detector, it generates a certain signal, and that signal is what we call these prompt phonons. Now, our detector is an insulator, so when it gets hit, it also breaks electrons out of the atoms that they're connected to. So they actually generate this cloud of electron holes, and one of the ways we operate our detectors are that we put a large field across the crystal. When the electrons see this field, they feel a force and they get dragged through the crystal onto the surfaces where they stop. Now, this crystal is not conducting, it's an insulator. So in order to move the crystal through it, the electron through the crystal, I actually need to drag that electron through. I need to do some work. And that work actually means the electron is banging into stuff as it's going through the crystal, and it's generating more phonons. And those are called Luke phonons. And so the total energy that I measure is the initial energy from the recoil, this purple phonon stuff, plus all of the Luke phonons that are created by dragging the electrons and the holes through the crystal. The amount of energy made by that dragging depends on the voltage. The higher the voltage, the more work I'm doing, and the more energy I'm going to deposit in the crystal. And so I have a nice little knob. If I turn the voltage up, I can make more of this Luke energy. If I turn the voltage down, I can make less. So by changing the voltage, I can either measure the amount of charges that are released by measuring the Luke energy predominantly, or if I turn it completely off, then I get almost no Luke phonons at all, and all I'm measuring are the nuclear recoil prompt phonons. So this is a really versatile detector, and we're going to take advantage of that. So this is what our detector looks like. It's called a high voltage EV scale resolution detector. We call it HPEV. It's about 1 centimeter by 4 millimeters thick. It has 2 TES sensors on it. So if you look at this detector here, it basically has an outer channel and an inner channel. You see all these little blue rectangles. Each one of those is one of those units that we were talking about before with one single TES, and they're all connected in parallel on the outer channel and all in parallel in the inner channel to make 2 channels. These detectors have single electron hole pair sensitivity. What that means is that we can see a single electron hole pair, and that gives us this peak right here in our energy. And if you then make 2 electron hole pairs, you get this peak in energy, and 3 electron hole pairs gives you this peak. So we can actually discriminate how many electron hole pairs were made in the detector from a particular given event. And that's really nice. It's an exceptional detector. It has a 2.7 EV baseline resolution. That's a world best resolution for this type of detector. The data that we took, we were able to set a threshold of 9.2 EV. So this is the minimum energy that we were sensitive to. And that's a world record for this type of detector. And we calibrated this detector down from 9.2 EV all the way up to hundreds of keV. And that's the first time a detector has had that large bandpass, that dynamic range. And we've been able to keep the good resolution at about the 5% level through that entire energy range. So this is the resolution in percentage, and you can see that is fairly flat. So it's a very interesting detector to work with. And we've done a couple of things with this detector. So one of the things that we did, and this was actually something that Ziqing was one of the people spearheading this effort, was to take these detectors to Duke University, where they have a neutron beam at the tunnel facility, and do a neutron beam calibration run to measure the physical properties of silicon when neutrons hit the silicon, how much charge is made. We also took data in my lab at Northwestern to characterize this detector before taking it to Duke and to do a dark matter search. I'm going to show you some of the results from this. And then we moved the detector to our Nexus facility, which we'll talk about in a little bit, and are taking data now. So the calibration is we just finished the analysis. We're going to publish it soon, and it's going to be the lowest threshold that this property called the ionization yield or quenching factor has ever been measured. And we're going to take data at Nexus starting in about 2 weeks. And we think that we've made some improvements to the system, and we expect to have a world best sensitivity in terms of the sensitivity to dark matter. So that's very exciting. So I'm not going to go through the details of how we go to a dark matter search. These are 4 different models for dark matter search, for dark matter, and what we're showing are exclusion curves. What this means is anything above one of these lines is excluded as a potential dark matter candidate for that detector. So if we took a dark matter that was, for example, 100 MeV and had a cross section, which is how often it would interact with an electron of 10 to the minus 27 square centimeters, that has been ruled out by all the experiments. Things over here in the white area have not been ruled out. So there might be dark matter models that exist, and dark matter might be here, and nobody has been sensitive to it yet. Now, I just finished telling you that we had this detector with all these world best qualities, and yet our limit is not the world's best. It wasn't as good as we wanted it to be. And so we started to say, well, what happened? Because we had better resolution, we had a better performing detector, we ran for longer. Why were we not able to make a better dark matter limit? So when we looked at our data, we saw that there were some really strange events that we had not seen before. So as I said before, a normal event will heat up and then cool back down. But what we saw was a bunch of little spikes following some of the events. And it took us a long time and a lot of data taking and analysis to understand what was happening. And we think we understand it now. And so our hypothesis was that the holder that we were using, these 2 pieces of PCB, so the crystal is right here in the middle. So these 2 pieces of PCB were scintillating. They contain silicon oxide. And here's some paper measuring the luminescence properties of silicon oxide. I won't go into the details. The point is that you can explain the time constants and the features of this signal as a luminescence signal from these holders. Now, that wasn't proof, it was still a hypothesis. So one of the things that you could do to try to figure out if this was really happening is to have more than one detector running at the same time. And so we went to the Nexus facility. This is a facility at Fermilab that we've started a few years ago in collaboration with Fermilab. There's a dilution refrigerator, which is 100 meters underground. It has a lead shield around it to get it to a nice low background. And it's a really nice facility for doing prototyping of detectors. And so what we did is we placed 4 detectors at Nexus. Here's Valentina and Ben closing up the fridge. And the detectors basically look like this. So we took 4 of the detectors and we placed them in a line. And there's a hole in this copper so that these guys can see each other. And so the idea is that if one of these PCBs is emitting light, it will shine light on this guy, but it'll also shine light on that guy. And maybe it'll bounce around and shine light on this guy as well. And so what we see, and this is very preliminary data, when you compare the data we took in the surface at Northwestern, this is the 1, 2, 3, 4, 5 electron hole pair peaks. And then we compare it with data taken at Nexus, where we have removed all events in which more than one detector fired. In other words, events that had a coincidence between one detector and another, which is what you would expect if there's some scintillation happening. We see a reduction of orders of magnitude in the number of events we see. So this is very exciting. This showed that indeed what we were seeing was something that was external to the detector, and that it was the scintillation hypothesis was very likely right. It also allowed us to take lower background data. And so we're analyzing this data right now. We're going to produce a new dark matter limit soon. But it's not just enough to say, oh, okay, well, now we can remove the events by looking at coincidence. Why don't we remove the thing that's doing the scintillation in the first place? And so we've redesigned our holder to have as little insulator inside the detector volume as possible. So now this is a CAD rendering of the design we made. And this is the first prototype that we built. We have everything is inside the detector stack is now copper. We have 4 of these detectors which we can place face to face. So they all 4, each one of the detectors sees the other 3 detectors. They're all facing each other. And here they are mounted at Nexus. They're inside these boxes. We're about to start taking data with these detectors. And if we are correct and we get rid of these burst events, well, these spike events afterwards, we should have world-leading sensitivity to dark matter. So we're very excited about this. We're about to start taking data in about 2 weeks. Okay, so now I'm going to switch gears and talk a little bit about neutrinos. So neutrinos are part of the standard model. They were originally postulated to explain radioactive decay. But as we talked about before, neutrinos have mass. We can see them change from one type of neutrino to the other. And that only can happen if they have mass. So neutrinos are part of the standard model, but they turned to the dark side. Neutrinos turn out to be dark matter. Why? Well, neutrinos do not interact with photons. They are dark and they have mass. So they are dark matter, except that they're not the dark matter. You can measure all of the mass contained in all of the neutrinos that exist in the universe, and you only get about 1% of the dark matter you need. So neutrinos are dark matter, but they're not the dark matter. They're more like the kid of the dark matter, or maybe like the grandkid of the dark matter. So for those of you that are Star Wars fans, they're kind of like Kylo Ren to Darth Vader. Now, these neutrinos are very interesting to study because they might be responsible for the matter-antimatter asymmetry in the universe. There are mechanisms by which we could explain why there is more matter than antimatter that involve neutrinos. So we would like to understand that. Also, all of the neutrinos that we have seen and detected are all left-handed, and it's a complicated quantum mechanical property of fundamental particles. I'm not going to go into it. The point is that all of the other particles we have sensed come in 2 ways. They come in 2 flavors. They come in the right-handed flavor and the left-handed and right-handed flavors. But only left-handed neutrinos have been observed. So if right-handed neutrinos exist, maybe we've never detected them before because they're harder to detect. One of those could be the dark matter. So there's still, we know that these particular neutrinos are not the dark matter, but it's possible that one of their cousins, if they exist, these right-handed neutrinos, also sometimes called sterile neutrinos, might be the dark matter. So that's another reason to study them. Now, neutrinos interact through the weak force. And we're going to look at a particular interaction called coherent elastic neutrino nucleus scattering. The short version of the story is that the neutrino interacts with the entire nucleus. And so it gives you a much, much higher rate than other types of neutrino interactions. but it also is like a ping pong ball hitting off a bowling ball. So it only gives the bowling ball a really tiny amount of energy. So it's very, very hard to measure. It allows you to make kilogram scale neutrino detectors as opposed to the existing ton scale detectors. But because of this very small recoil energy, people only saw this for the first time a few years ago. So what we're going to do is we're going to use our TES technology to measure the spectrum of this process at a reactor. A nuclear reactor produces many, many neutrinos. We're going to put our experiment very close to the neutron reactor, and we're going to measure this reaction spectrum. The reason that it's interesting is because if there are physics beyond the standard model, depending on the type of physics, those new particles or new interactions can change the spectrum. And so by measuring the spectrum, doing a precision measurement of the spectrum, you're sensitive to new physics. The experiment looks something like this. This is a cryogenic system with a lot of shielding, and it's placed about 8.8 meters from the nuclear reactor core. This is a nuclear reactor in France, in Grenoble, called the ILL. We are putting a lot of lead shielding and polyethylene shielding around the detector because we're at the surface and there's a reactor and there's lots of particles that are not the neutrinos that we want to sense that are flying around. So we want to shield our detector from all that other stuff. We also have some shielding inside the cryostat. And then underneath that shielding, we're putting our stack of detectors. And we're planning to put about 1 kilogram of detectors in Ricochet. We're planning to start taking data in 2023 as well, and expect to have our first measurement in 2024. To use the TES technology, we've developed this architecture of modular cryogenic detectors where we've made all of the hard stuff, the thermometer, into this chip that we are going to place in a holder. And then the target is placed in sapphire spheres and just has a gold layer deposited on the top. You can put a wire bond between the TES and this target, and the heat from an event when it hits the target flows through the wire bond to the TES, which then senses it, goes through another wire bond back to the fridge where it then gets cooled down. And this, we've made a design, we've made a model of this, we've had predictions of how this is going to work. We've made these complicated shapes to engineer the thermal structure and place the TESs and have the wire bonds connect. We've made these housing that's sort of a prototype housing for this. So we're all getting ready to do the first measurements on these in about a month or two. These chips are actually in the last stages of fabrication right now. And the nice thing is, because of this modular design, we can use whatever target we want. So for Ricochet, where we're doing coherent scattering, we're going to use silicon, germanium, and zinc as targets. For neutrinoless double beta decay, which is a different type of neutrino experiment, we can use scintillating targets and still read them out in the same way. So this is a really nice technology because it not only allows you to mount many, many detectors very easily, but it allows you to change out the target very easily and is thus being utilized in more than one experiment. And these chips can be fabricated in a standard 6-inch wafer, and you can get about 1,000 chips in a 6-inch wafer. So we can make many of them, and it's a very scalable modular design. Okay, and I'm going to finish off by talking about one more thing. So here's the bridge of a Star Destroyer, and here are all the computers that are being used to run the Star Destroyer. And if you look very closely, you'll notice that each of these is a quantum computer. You can tell by the little lights that are blinking. And so the last thing I'm going to talk about is quantum computing. So this is the Google Sycamore system. So this is their fridge. And this is the Sycamore chip. It has 52, I think, 50-some qubits in it. This paper that was published by the Sycamore team is showing their results where they have measured these events that break the coherence over the entire chip. And what they, after studying them, what they found was that photons going through the detector or through the chip are hitting the silicon substrate, and they're creating phonons. These phonons are breaking quasi-particles in their superconducting structures, which are then affecting their qubits and leading to the coherence of their qubit chips. Now, this may look a little bit familiar because this is kind of what we do, right? If you look at that picture, you look at this picture, you know, they're pretty similar. We sense phonons with our superconductors, which are then sensed out by these detectors. We have these chips and we can sense the phonons going on it. We have fridges that can be wired up with all these RF lines to qubits. So it turns out that we have all the tools needed to work on this problem, and we are. So this is the Nexus facility, and all of these guys right here are all RF lines that are connected to a 4-qubit system that we installed down here. And we're in the process of doing studies of how radiation shielding affects the coherence time in qubits. And so we basically, this is really a particle detector problem. And that's where our expertise are. So we're bringing our knowledge of cryogenics and particle detection and quasi-particles to quantum computing. This is a new effort that we started in collaboration with the Quantum Science Center. We are operating this at Nexus in Fermilab. We are also building a brand new fridge at Fermilab underground, actually right next to Nexus. So Nexus is sort of the prototype where it's going to be fully dedicated to underground quantum computing. And so this is a new effort that I've started in collaboration with other folks at Fermilab. And we're very excited to both bring our expertise in particle physics and low backgrounds to quantum computing. At the same time, we're also looking at ideas for using quantum sensing and qubits as particle detectors. And so we're looking at both sides of it. What can we do for quantum computing, but also are there new interesting ways that we can use qubits and the sensitivity of these new technologies for future searches for dark matter? So I'll end here saying that most of our work has been up to now looking for dark matter. We've had new dark matter limits from Northwestern, and we made these ionization measurements at Duke. We are now preparing for a new dark matter run at Nexus. At the same time, we are working on neutrino physics on the Ricochet and Cupid experiments with these new architecture that's very modular and in principle can be deployed with thousands of detectors. And this is R&D for Ricochet, which is going to deploy next year, but also for future neutrinoless double beta decay experiments. And finally, we're taking all of the know-how from this work and applying it to low background quantum computing underground, testing qubits in low background shielded environments, and developing an R&D program, not just for shielding, but also for active sensing of radiation. You can put active vetoes around a quantum computer, and even then engineering the quasi-particles on chip to try to siphon away the heat from the qubits and sink them into other structures on a quantum computing chip that are there to prevent the chips from seeing most of the energy deposited when photons arrive. So that's an entire R&D program that we're starting, and we're very excited about it. And with that, I'll finish, and I'll hopefully take some questions.